From heavy Volvo high-lift loaders feeding massive log yards, to fully automated mills turning raw timber into precision boards, this is modern wood power. Watch bark strip, cants shaped, boards sorted, and engineered wood transformed into buildings that rise fast and strong. Technology, control, and serious productivity. Welcome to the new era of timber. The Volvo L2000H high lift was chosen for one reason above all else. It's built to work hard, day after day, without compromise. In Austria, it stands at the gateway of the sawmill, meeting every truck and every load with calm strength. With its higher load capacity and reinforced structure, it isn't just moving timber, it's protecting uptime, extending service life, and earning trust over years of operation. From the factory entrance to the heart of the plant, the L2000H keeps material flowing, handling thousands of cubic meters of timber with a consistency that keeps production running smoothly. Its advanced high-lift system and redesigned grapple give the operator precision and confidence, keeping loads steady even while traveling, and helping every movement feel controlled and deliberate. Inside the cab, technology quietly works in the background. The co-pilot system blends camera views, assistance functions, and collision mitigation features into one smart safety net, alerting the operator and stepping in when it matters most. Automatic braking, obstacle detection, and powerful LED lighting create a safer workspace around the clock, even in crowded or low visibility environments. Backed by strong service support and designed for reliability, the Volvo L2000H high lift isn't simply a machine in the log yard, it's a key partner in production. Durable, stable, and dependable, it delivers the performance that keeps the sawmill moving forward. Columns Lumber Products is more than just a sawmill. It's a modern, tightly coordinated system, a place where decades of lumber-making experience meet advanced automation, digital scanning, and careful planning. Every day, thousands of logs arrive here and begin a transformation. By the time they leave, they've become accurately sized, precisely processed lumber ready for construction, manufacturing, and countless other uses. What makes this operation impressive isn't just the machinery. It's how every decision, every movement, and every cut is driven by optimization, squeezing the most value from every single log while reducing waste and improving consistency. The journey begins before a log ever touches a saw. Loaded trucks roll onto the property and pull up to the scale house. Here, the numbers start telling the story. Each truck is weighed as it arrives, recording the full load. When the wood has been unloaded and the driver returns, the truck goes across the scales again. The difference between the two figures becomes the official net weight, the amount of usable timber delivered. It's simple in concept, but critical in practice. The system ensures transparency, fair compensation, and accurate tracking of inventory. On average, each truck delivers around 26 tons of raw material, enough wood to feed an incredibly busy production line. From there, the logs meet the sawmill crane. It works with steady precision, unloading truck after truck, sorting and distributing material. Some logs move straight into production. Others are placed neatly into the log pile, which serves as a strategic buffer. Even if deliveries slow down for a day, production doesn't stop. Operators constantly balance freshness, volume, and inventory, usually pulling the older wood first to maintain quality, while always keeping enough material staged for smooth flow. As logs begin entering the mill, the transformation truly starts. Before cutting, bark is stripped away. The debarker removes the tough outer layer that would otherwise damage blades and affect final product quality. Rather than discarding it, the bark becomes a resource, collected, loaded, and reused as fuel in industrial applications. Nothing here is treated carelessly. Almost every byproduct finds another purpose. Once cleaned, each stem moves toward one of the most intelligent systems in the mill, the merchandiser. This station represents the heart of optimization. High-speed laser scanners map every inch of the log, building a three-dimensional model. The software analyzes taper, curves, knots, and shape, then calculates how to extract the maximum value. Sometimes that strategy means cutting several shorter pieces. Other times it means preserving as much length as possible. And if a stem meets strict size and quality standards, it may even be selected to become a utility pole. Whatever the decision, the instructions are sent automatically to the saw line, ensuring every cut is deliberate instead of guessed. From here, logs flow along different paths based on their size and characteristics. Some move toward the double-length infeed, while the biggest pieces, massive stems close to 42 inches in diameter, head to the carriage saw. The carriage is where tradition meets technology. Lasers determine the best cutting pattern, but an experienced operator remains in control, guiding the log back and forth while the vertical band saw peels slabs away. Those slabs don't go to waste. They head to the horizontal resaw, where 1 and 2 inch boards are recovered until nothing usable remains. Only when the wood cannot produce lumber anymore does it become chips. Meanwhile, logs routed through the DLI enter the reducer twin. Here, precision engineering reshapes the log into a form that can be processed efficiently. The wood is scanned, rotated, and positioned so its natural bend is used to its advantage, rather than fought against. Chip heads and saws flatten 2 parallel faces, removing sideboards while forming what is now called a cant, the square core of the log. That cant moves on to the curved saw gang, one of the most sophisticated systems in the mill. Instead of forcing the log to fit a straight cut, the saws literally follow the natural curvature of the wood. This technology dramatically increases recovery, turning shapes that would once have created waste into usable lumber. With multiple saws running top and bottom, each pass produces a blend of boards and thin pieces, while side chippers clean and capture anything that still holds value. Once boards leave the primary breakdown systems, the focus shifts from shaping logs to refining lumber. Pieces with rounded edges move to the edger, where scanners again analyze width and defects. Adjustable saws square them up, trimming away only what's necessary. Those small pieces are chipped and recycled. Boards already square proceed directly toward the trimmer line. At the trimmer, length becomes the priority. Each board is scanned, evaluated, and positioned so the least amount of material is sacrificed while still meeting quality standards. Saws cut in fixed increments, guided by automated fences that make precise adjustments in fractions of a second. Anything that doesn't meet grade gets another chance, sent back to the edger for rework rather than discarded. What emerges is neat, dimensional lumber, but it's not finished yet. Boards now flow into the sorter, a towering, rhythmic system that seems part machine, part choreography. Here, every piece is automatically grouped by thickness, length, and width. Bins quietly fill until each one reaches capacity. When full, entire bundles are released and carried to the stacker. The stacker carefully builds packs layer by layer, inserting spacer sticks between each course. These sticks may look insignificant, but they are essential. They create channels for air movement during kiln drying. Without them, moisture would escape unevenly, creating warped, twisted lumber. Forklifts transport freshly stacked packs to the green yard. They rest only briefly, usually less than a week, before entering the kilns. Inside, controlled heat gently draws moisture from the wood, stabilizing it and preparing it for its final shaping. Once dried and planed smooth, the lumber is ready. Trucks will carry it out in the same way logs once arrived, beginning an entirely new chapter in homes, buildings, and projects far beyond the mill gates. From the moment a truck rolls across the scales to the final stack of finished boards, Column's Lumber Products demonstrates what a modern sawmill can be: efficient, data-driven, environmentally conscious, and relentlessly focused on maximizing the potential of every tree. Here, technology doesn't replace experience, it amplifies it. And the result is a process where raw timber becomes high-value, precisely manufactured lumber through a seamless blend of tradition, innovation, and respect for the resource. An oriented strand board plant, often simply called an OSB plant, is a place where engineering, chemistry, and wood science come together. What enters the facility as raw logs leaves as strong, uniform structural panels used in homes, buildings, and large construction projects around the world. OSB may look simple from the outside, but every panel is the result of carefully controlled decisions about moisture, temperature, pressure, and fiber orientation, all designed to produce strength, stability, and cost efficiency. The story begins with the logs themselves. Only certain species and sizes are selected, chosen for fiber quality and consistency. After arriving at the plant, the bark is removed to protect downstream machinery and improve the final panel surface. Then the logs are reduced into long, ribbon-like strands using high-speed flakers. These strands, typically between 40 and 100 millimeters long, form the structural threads that give OSB its internal strength. Once created, the strands aren't ready yet. They contain natural moisture that must be carefully reduced. Inside large rotary dryers, heated air circulates through the material, steadily bringing moisture down into a narrow, ideal range, usually between 3 and 7%. This isn't just for efficiency. Drying ensures that resin and wax will adhere properly later in the process, and that panels won't swell or weaken in service. After drying, the strands pass through screening systems. Oversized pieces are refined, fines and dust are removed. What remains is clean, uniformly sized material, ready for blending. Here, chemistry joins the process. In enclosed mixers, strands are gently tumbled, while precise amounts of adhesive resin and wax are applied. Modern plants commonly use MDI or phenolic resins, formulations designed to create strong bonds while meeting environmental and emission standards. The wax adds an important layer of moisture resistance, helping finished panels perform well in roof decks, walls, and subfloors exposed to changing conditions. Next comes one of the most defining stages: forming. Conveyors distribute the coated strands into wide, moving mats. Specialized orienters align the strands intentionally, not randomly. The outer layers are oriented along the panel's length to carry bending loads, while inner layers may be oriented crosswise to resist shear and enhance dimensional stability. What looks like loose wood at this point is actually a carefully engineered structure. That mat then meets the heart of the plant, the press. Under intense heat and pressure, resin cures, fibers compress, and the loose mat transforms into a solid board. Many modern facilities use continuous hot presses, where the mat moves steadily between heated platens. This approach produces smoother thickness control, improved density profiles, and higher overall output. In only moments, thousands of strands lock together as one engineered panel. Emerging from the press, the panels are still hot and must cool and stabilize to maintain dimensional accuracy. Once conditioned, they move to finishing lines. Precision saws trim edges and cut standard dimensions. Sanding systems refine the surface, preparing panels for easier installation and better adhesion when finishes, membranes, or flooring layers are applied. Automated stacking and bundling organize panels efficiently for storage and shipment. Behind all this machinery is a continuous stream of data. Sensors and control systems monitor strand moisture, resin application rates, mat weight, press temperatures, and panel thickness. Operators watch trends, make adjustments, and keep production balanced, always aiming for consistency and minimal waste. From raw wood to finished panel, An OSB plant operates like a finely tuned ecosystem. Mechanical preparation, resin chemistry, heat, pressure, and precise orientation all work together to produce a board that is strong, stable, and reliable, ready to help build the walls, roofs, and floors of modern structures. At Veneer, veneer production is treated almost like craftsmanship carried out on an industrial scale. Every step carefully controlled to protect quality and maximize the value of each log. The journey begins as logs arrive at the mill and are cut to precise lengths, matched to the type of veneer that will eventually be produced. After cross-cutting, the bark and surface contaminants are removed, protecting the machinery and ensuring the wood beneath remains clean and free of defects. Where needed, bandsaws shape and square the log, creating geometry that will allow smooth, uniform slicing. Before the first sheet is ever cut, the wood is gently prepared. In large steaming vats, heat and moisture penetrate deep into the fibers, softening them and making the log more flexible. This conditioning reduces cutting stress, prevents cracking, and preserves the natural beauty of the grain. From there, the logs move to the slicing machines, the true heart of veneer production. With precise, controlled movements, the blade peels away thin sheets, each one consistent in thickness and surface quality. A stay-log mechanism supports what remains of the core, stabilizing it so usable veneer can be recovered all the way to the center. Fresh veneers then travel to the clipping line, where edges are trimmed, flaws removed, and sheets brought to exact dimensions. Skilled operators and automated systems work together to grade each piece, assigning it to the applications where it will perform best, from decorative surfaces to high-performance engineered wood. Finally, the finished veneers are stacked, organized, and stored with care, maintaining traceability and protecting the delicate sheets until they move on for further processing or shipment. At Veneer, precision, control, and respect for the raw material come together, turning solid logs into high-quality veneer that carries the natural character of wood into its next life. The Serrafita Geminata Tercero Corte Conjugata compact line is designed for a very specific challenge in modern sawmilling, extracting the greatest value from small-diameter pine logs while working inside limited space. Built for logs between 1 and 3 meters long and roughly 10 to 20 centimeters in diameter, it delivers full industrial performance within a compact footprint, making it ideal for mills where every square meter matters. At the heart of the system is its unique cutting concept. A twin band saw performs 2 synchronized longitudinal cuts, removing the side slabs in one smooth motion. At the same time, a conjugated third cut divides the center section with precision. Instead of multiple passes and repeated handling, the machine shapes the log into a stable cant in a single operation. The result is smoother flow, fewer bottlenecks, and greater dimensional stability. The structural design supports that performance. Although lightweight and easy to install, the frame is engineered for rigidity, absorbing vibration and maintaining accuracy even at higher feed speeds. Ultra-thin kerf blades further enhance efficiency, converting more wood into usable product and less into sawdust, an important advantage when dealing with smaller logs. Energy efficiency is another defining feature. Optimized drive systems and carefully balanced power transmission reduce electrical. The Serrafita Geminata Tercero Corte Conjugata compact line is built around a very specific challenge: how to process thin pine logs quickly, accurately, and economically, even in limited industrial space. Designed for logs between 100 and 200 millimeters in diameter and lengths from 1 to 3 meters, it delivers full production capability while keeping the layout compact, simple, and easy to maintain. At the heart of the system is its unique cutting concept. A twin bandsaw removes both side slabs at the same time, while an integrated third conjugated saw performs the central cut, all in a single pass. Instead of stopping, rotating, and feeding the log again, the compact line completes the breakdown immediately. The result is a stable cant, fewer handling stages, and a smoother, faster production rhythm. The structure itself is engineered for precision. Lightweight but rigid, the frame absorbs vibration without adding unnecessary mass, allowing high feed speeds while maintaining tight dimensional tolerances. The stability of the assembly helps the saws run cleaner, producing straighter cuts and improving the quality of downstream operations. Efficiency is woven into every component. Ultra-thin kerf band blades recover more usable wood from each log by turning less fiber into sawdust. Optimized drive systems and carefully matched power transmission lower electrical demand, reducing operating costs over thousands of production hours. With synchronized saw alignment and precise feed control, the machine consistently delivers smooth surfaces and repeatable dimensions, shift after shift. For operators, that means fewer adjustments, less rework, and predictable output. Altogether, the Serafita Geminata Tercero Corte Conjugada compact line represents a practical, performance-driven solution for thin log processing, combining compact design, technical accuracy, and economic efficiency to help modern sawmills get the most value from every piece of wood that passes through the line. During the construction of the new production hall for I+R Holzbau in Lauterach, something remarkable took place. Instead of relying on conventional softwood structures, the project team chose a cutting-edge engineered timber product for the primary frame of the building, baobouche. Every major beam and the entire roof system is formed from this high-performance material, a clear statement about where modern timber construction is heading. Baobouche is not timber in its traditional sense. It's a laminated veneer lumber made from European beech. Thin layers of veneer are precisely aligned, glued, and pressed under tightly controlled industrial conditions. The result is a dense, extremely strong structural material that behaves consistently and predictably, a quality that engineers and architects value deeply. For decades, structural timber has been almost entirely dominated by softwood species, such as spruce or pine. Hardwood was impractical, too difficult to process, and too heavy to use efficiently. But advances in engineering and processing have changed that picture completely. With baobouche, beech can now be transformed into high-performance structural members, capable of carrying significantly higher loads than comparable softwood elements. Because of its exceptional strength and stiffness, baobouche allows slimmer cross-sections and more elegant proportions. Less material is needed, yet structural capacity increases. This opens new architectural possibilities, especially in buildings where the structure is intentionally left visible and becomes part of the interior design language. The roof of the I+R Holzbau Hall demonstrates this advantage clearly. Prefabricated baobouche roof panels were produced in a controlled factory workflow. Each component was positioned using precise templates, ensuring repeatable accuracy while dramatically speeding up production. Panel after panel could be manufactured in a short time frame, all with consistent quality and minimal tolerances. This high degree of prefabrication paid off once construction reached the site. Instead of long installation phases, the structural elements arrived ready to assemble. Cranes lifted the prefabricated beams and panels into place, and connection points fit exactly as planned. In just 2 days, the entire hall structure stood complete, reducing noise, disruption, and weather exposure. What remains is not only a functional production building, but also a demonstration project. It shows how baobouche bridges engineering efficiency, architectural refinement, and sustainability. By combining the natural resource of hardwood with modern manufacturing technology, I+R Holzbau's new hall points toward the future of industrial and commercial timber construction, lighter, stronger, faster, and more resource-conscious than before. Hoho Vienna, rising 84 meters above the city, demonstrates how high-rise construction can evolve when timber engineering and modular thinking come together. The tower is conceived as a hybrid system. A reinforced concrete core provides lateral stability and fire protection, while the outer structure is formed from elegant glued laminated supports and cross-laminated timber panels. Together, they create a rigid yet lightweight frame that celebrates wood as both structure and architecture. Much of the project is built long before it reaches the construction site. In specialized production facilities, components are fabricated under factory-controlled conditions. At Hermagor alone, roughly 400 cubic meters of glulam elements are produced, block-glued, reinforced with ribbed steel, and engineered for strong, tension-resistant connections to adjoining concrete components. Surfaces are precisely cut, sanded, and protected, with double coatings to limit soiling and yellowing, preserving the warm appearance of the wood over time. The prefabrication strategy goes further. Vapor barriers, window units, and detailing are installed directly in the factory. This reduces unpredictable on-site work, improves accuracy, and ensures consistent quality. When the modules arrive in Vienna, they fit together with remarkable precision, allowing floors to rise quickly and efficiently with minimal exposure to weather. By combining advanced glulam and CLT fabrication with modular logistics and hybrid engineering, Hoho Vienna shows how tall buildings can become faster to assemble, structurally robust, and visually refined, pointing toward a future where timber plays a central role in sustainable high-rise construction. The cross-laminated timber project in Japan is a striking example of how modern engineered wood construction and advanced prefabrication techniques are reshaping the building industry. At the center of the system is CLT cross-laminated timber, a material created by laminating multiple layers of lumber together, with each layer's grain rotated perpendicular to the one below it. This cross pattern doesn't just look technical on paper, it transforms ordinary lumber into large, solid structural panels with impressive stiffness, dimensional stability, and strength. Because of this, CLT panels can safely serve as load-bearing walls, floor systems, and even roof structures in multi-story residential buildings. Their engineered makeup helps control shrinkage and deformation, allowing architects to design with a high level of precision while still working with natural wood. The journey of each panel begins long before it reaches the job site. Production starts in the factory, guided by detailed architectural and structural models created in digital design software. Raw lumber is carefully dried, sorted, and graded to ensure consistent quality. From there, boards move through automated production lines, where they are trimmed, oriented in alternating directions, coated with adhesive, and pressed under high pressure to form large, monolithic panels. Once panels cure, another layer of precision work begins. CNC machining equipment cuts out openings for doors, windows, staircases, and mechanical penetrations. Every notch, groove, and fastening point is prepared in a controlled environment where accuracy can be measured down to millimeters. This level of prefabrication dramatically reduces the amount of work needed later on site. When fabrication is complete, panels are labeled, wrapped, and transported to the construction site using a just-in-time delivery schedule. Instead of storing piles of materials around the project, panels arrive as they are needed. Cranes lift each piece into place like parts of a giant, three-dimensional puzzle. Construction typically starts with the ground floor walls, then progresses upward as floors and walls interlock. Because each panel covers large areas at once, entire sections of the building can rise in only a few days. On site, precision matters. Crews work carefully to align edges, secure connections, and verify tolerances. Specialized metal connectors, screws, and bolts link the panels together to create a continuous structural system capable of resisting wind, vertical loads, and Japan's frequent earthquakes. Expansion joints and seals are installed, protecting against moisture while maintaining performance. Mechanical, electrical, and plumbing systems slide into place with minimal cutting, because most pathways were planned earlier in the design stage. This reduces damage risk, speeds installation, and helps maintain the structural integrity of each panel. One of the biggest advantages of CLT is how much work shifts from outdoors to indoors. Since panels are manufactured in a factory, construction becomes less dependent on weather and requires fewer on-site workers. Waste is significantly reduced, machinery noise is minimized, and the site remains cleaner and more organized. At the same time, the solid wood panels naturally provide good thermal mass and acoustic comfort, helping create quiet, energy-efficient living spaces. As structures rise, the benefits become visible not only in speed, but in the rhythm of construction itself. Where traditional builds may take months to frame, CLT structures can reach structural completion in a fraction of the time, allowing follow-on trades to begin earlier and overall schedules to compress. In Japan, where precision, efficiency, and seismic safety are paramount, CLT is gaining strong momentum in multi-unit residential developments. It delivers the strength of engineered systems, the warmth and sustainability of wood, and the efficiency of industrialized construction. Together, these qualities offer a modern alternative to conventional concrete and steel, one that supports faster building timelines, reduced environmental impact, and a new architectural language rooted in advanced timber engineering. The Madureira Matosanda Sawmill represents a modern, high-capacity timber processing facility, purpose-built to handle thick, heavy logs with reliability, precision, and efficiency. At the heart of the operation is a full line of robust mill industrials machinery, designed specifically for demanding industrial production. Together, these systems allow the mill to process large volumes of raw logs while maintaining tight control over quality and yield. Operations begin long before a log ever touches a saw blade, Everything starts in the log yard, the main receiving and staging area for incoming timber. Trucks arrive loaded with logs harvested from regional forests, and each load is carefully unloaded and inspected. Logs are sorted according to species, diameter range, straightness, and production priority. This organized buffering area works like a reservoir of raw material, ensuring the saw line always has wood available. Even during busy intake periods, production can continue smoothly without interruptions. From here, logs move toward the infeed deck, where they are positioned and aligned. The goal is not only to move wood forward, but to prepare it properly for cutting. In many modern sawmills, including facilities like Madisonda, debarking is carried out before the first major sawing operation. Removing bark helps protect blades from grit, stones, and sand that can become embedded in the outer layer of the log. The result is cleaner cuts, less tool wear, and longer intervals between maintenance. Before the primary sawing phase, the log is carefully centered and oriented. Operators and automated systems work together to determine the best cutting geometry, taking into account taper, curvature, and natural defects. Small adjustments at this stage can make a huge difference, influencing lumber recovery, dimensional accuracy, and the overall value obtained from each log. Primary breakdown is where the real transformation begins. Heavy-duty horizontal and vertical band sawmills, engineered for high-density, large-diameter timber, slice the logs into flitches or cants. These sawmills use thin kerf blades, meaning the cut itself removes less material, less sawdust is produced, and more of the tree becomes usable lumber, which significantly increases yield over time. The saw heads travel along rigid, precisely aligned rails, ensuring stable motion even under heavy loads. Throughout the process, operators continuously monitor alignment, adjusting cutting paths to follow the log's natural shape and maximize every centimeter possible. Once the log has been reduced into manageable sections, the material travels to secondary processing. Here, multi-blade saws and gang saw lines refine the rough cants into boards of specific thicknesses and widths. Whether standard 1-inch construction boards, heavier 2-inch structural pieces, or specialty dimensions for custom orders. This stage focuses heavily on repeatability and accuracy, producing lumber that meets both dimensional tolerance and visual grading requirements. Supporting all of this is a network of automated conveyors, transfer decks, kickers, and sorting tables. These systems keep material moving smoothly from one station to the next. They minimize manual lifting, improving worker safety, while also maintaining consistent production rhythm. In advanced configurations, scanners and computerized controls analyze each piece of wood in real time, detecting knots, defects, and variations in diameter. Cutting programs then adjust automatically, making decisions that once depended entirely on operator intuition. As lumber exits the sawing lines, it enters the finishing, sorting, and stacking phase. Boards are grouped by length, thickness, and grade, then arranged into uniform bundles. For lumber that still requires drying, spacer sticks, known as stickers, are placed between each layer to create ventilation pathways. This spacing is critical for both natural air drying and controlled kiln drying, preventing warping and moisture pockets. Once properly stacked, each bundle is compressed and secured using steel or high-strength polymer straps, producing stable, transport-ready packs. Throughout the facility, the integration of Mill Industria's technology demonstrates how mechanical strength and intelligent control systems can work together. Modular cutting stations allow the mill to adapt quickly to different log sizes and species. Precision motion control ensures smooth, consistent cutting. And durable construction guarantees that equipment remains reliable even under continuous industrial-scale workloads. In the end, the Madureira Matasuunda sawmill stands as a clear example of what defines contemporary heavy log operations: high throughput, optimized material recovery, consistent quality, and machinery built to endure years of demanding service. It shows how modern sawmilling is no longer just about cutting wood. It is about engineering efficiency, maximizing natural resources, and producing uniform, high-value lumber through carefully coordinated technology.